The study of extreme events, EEs, is crucial in various scientific and interdisciplinary disciplines due to their immediate severe consequences and potential applications. EEs are unpredictable, spontaneous, and have disastrous impacts on socioeconomic situations. They can be natural, such as floods, tsunamis, earthquakes, cyclones, droughts, seismic activity, wildfires, and volcanoes, or human-made, like power blackouts, nuclear leaks, regime shifts in ecosystems, and share market crashes. In the context of dynamical systems, EEs are defined as events with amplitudes larger than 4 to 8 times the standard deviation from the mean state or those appearing in the 90th–99th percentile of the probability distribution. These events occur far away from the mean state, appearing on the tail of the distribution with less frequency of occurrence. This research focuses on the rotational dynamics of a two-dimensional forced damped pendulum under the influence of AC and DC torque. The pendulum's length is found to significantly affect the system's behavior, with a specific range causing intermittent extreme rotational events that deviate significantly from a well-defined threshold. The statistics of the return intervals between these extreme rotational events are supported by the data to be spread exponentially. Numerical results show a sudden increase in the size of the chaotic attractor due to an interior crisis, which is the source of instability responsible for triggering large amplitude events in the system. Additionally, phase slips are observed with the appearance of extreme rotational events when the phase difference between the instantaneous phase of the system and the externally applied AC torque is considered. The study offers valuable insights into the emergence of extreme rotational events in dynamical systems and may find applicability for a better understanding of continuous time systems with a strange attractor. I apologize, but the provided content appears to be a mix of unrelated words and phrases, making it challenging to refine into a coherent summary of a research paper. To assist you, could you please provide the actual content from the research paper that needs refinement? I'll be happy to help you transform it into a concise, technically accurate summary suitable for voiceover narration. The study examines extreme rotational events, ArXiv, in a pendulum model, focusing on the impact of varying pendulum length L. The bifurcation diagram in Figure 3 illustrates the transition between librational and rotational motions, with rotational motions being the primary focus due to their higher maximum values for a wide range of L. Rotational events are classified into two categories: librational events for Qmax less than 0.5 and rotational events for Qmax greater than 0.5. A subset of rotational events are identified as ArXiv when their amplitude exceeds a threshold value, ht equals m plus d sigma, d squared rnf 0 grams, where m and sigma signify the mean and standard deviation of a collected dataset of rotational events, respectively. The choice of d, set to 6 in this study, determines how far the deviation is from the mean state and is chosen to sustain the extreme rotational events characterization. The study's essential characteristic is the irregular occurrence of ArXiv, classified based on the low probable occurrence of these events, which depends on the larger value of d chosen. Numerical simulations were performed by integrating the pendulum equation using the fifth-order Runge-Kutta-Felberg method with an integration step length of 0.01. The generation of ArXiv is examined in the context of varying pendulum lengths within the range 0.998, 1.004. Initially, periodic dynamics of oscillation are observed, followed by a transition to chaotic behavior after a certain value of L. This sets the stage for further analysis on the statistical properties of ArXiv and their implications for understanding complex systems. The emergence of extreme rotational events, ArXiv, in a forced damped nonlinear pendulum is investigated through numerical simulations. A bifurcation diagram of the maximum angular velocity, Qmax, is plotted against the pendulum's length, L, which serves as the bifurcation parameter. This reveals a sudden transition from chaotic oscillation to large amplitude chaotic oscillation at a critical value of L, denoted by L, and another transition from small amplitude chaotic oscillation to large amplitude chaotic oscillation at a critical value of L, denoted by R. Simulations are performed using the RKF45 method with an integration step length of 0.01 and 8 times 10 to the power of 5 iterations, leaving a transient of 3 times 10 to the power of 5 iterations. The pendulum exhibits librational dynamics for Qmax less than 0.5 and rotational motion for Qmax greater than 0.5. The ArXiv qualifying threshold line, HT, is plotted in red, and intermittent, sporadic blue points from the post-crisis attractor cross the red threshold line HT from the left and right sides, respectively. Results show that the amplitude of the chaotic attractor increases after crossing a particular value of L, and the pendulum swings back and forth as well as whirls over the top in a chaotic fashion. Beyond a specific value of L, the system dynamics exhibit chaotic libration, and the pendulum swings only to and fro due to the combined effect of DC and AC torque being inadequate to overcome its increased rotational inertia. Temporal dynamics of Q and the corresponding phase space, QQ, in the cylindrical surface are displayed for 5 different values of L. For L equals 0.999941, the temporal evolution of Q exhibits large amplitude oscillation, but no large spikes or bursts are observed, and no rotational events exceed the threshold. For L equals 0.999945, occasional large spikes are observed, and 2 rotational events that cross the red threshold line HT are treated as ArXiv. Phase space diagrams show that the trajectory bounds within a small portion of the periphery and rotates the entire cylindrical surface for L equals 0.999941. For L equals 0.999945, the trajectory is observed in the librational and rotational orbit, and the trajectory rotates within a bounded region during rotation but occasionally travels far away from the region, indicating the appearance of ArXiv. For L equals 1.001, ArXiv are not observed anymore, and the trajectory's deflection from a bounded region in the phase space is absent. The variation of HT by changing L is plotted in Fig. 3 for identifying ArXiv. Results demonstrate that the emergence of ArXiv is caused by the interior crises, and the pendulum's dynamics exhibit chaotic libration and rotation beyond specific values of L. Parameter values used in the simulations are W equals 0.25, F equals 2.27, M equals 1.0, G equals 1.0, gamma equals 0.75, T0 equals 0.7167, and T equals 0.4. The initial condition is fixed at Q0 equals 0.01, 0.02, and the results remain qualitatively the same for other choices of initial conditions. This study highlights the importance of understanding the emergence of ArXiv in nonlinear systems and provides insights into the complex dynamics of the forced damped nonlinear pendulum. The results have implications for the analysis and control of nonlinear systems in various fields, including physics, engineering, and biology. The paper explores the emergence of extreme rotational events, AIR, in a chaotic pendulum system through interior crisis. It analyzes the bifurcation diagram, revealing sudden and abrupt jumps of chaotic attractors at critical values of the bifurcation parameter L. These jumps correspond to the appearance of ArXiv, as observed in temporal dynamics and phase spaces. Temporal evolutions of the pendulum's angular velocity Q show intermittent large spikes, indicating ArXiv, near the crisis points L and R on the bifurcation diagram. Phase spaces reveal trajectories that traverse the cylindrical surface far away from their regular rival paths during rotation, leading to the formation of ArXiv. The paper highlights that the interior crisis is responsible for the generation of EREs in the system. This process involves a chaotic attractor colliding with the stable manifold of a chaotic saddle, resulting in intermittent behavior and the sudden enlargement of the attractor. The paper also explores how chaotic librational dynamics transit to chaotic dynamics consisting of both libration and rotation as the value of L changes. In conclusion, the paper demonstrates that ArXiv arise in the pendulum system due to interior crisis, a well-known phenomenon in dynamical systems where chaotic attractors undergo sudden qualitative changes depending on system parameters. The findings provide insights into the complex dynamics of chaotic pendulums and their potential applications in understanding extreme events in various physical systems. The temporal dynamics of the pendulum system are characterized by the occurrence of extreme rotational events, AIR, and phase slips. Figure 5 illustrates the time evolution of the pendulum's angular velocity and phase difference for 2 distinct pendulum lengths, L equals 0.999945 and L equals 1.00218. The upper panel shows the time series of the pendulum's angular velocity, q, for both lengths, while the lower panel displays the corresponding phase difference, d, with respect to time. For L equals 0.999945, a large amplitude rotational event is observed, accompanied by a phase slip indicated by the abrupt jump in the phase difference plot. Similarly, for L equals 1.00218, at the crisis point r, the time series and phase difference plots exhibit a phase slip during the transition from libration to rotation. The authors analyze the statistics of ArXiv by gathering data over 1011 time units, discarding the initial transient of size 106. Histograms are plotted for L equals 0.999941, before the crisis point L, and L equals 0.999945, just after the crisis point L. The data is divided into two groups, rotational motion and librational motion, with a red dashed line HT marking the threshold to distinguish between extreme rotational events and chaotic oscillations. The data for L equals 0.999941 does not cross the threshold, indicating no ArXiv in the pre-crisis regime. However, the data for L equals 0.999945 crosses the threshold, confirming the presence of ArXiv anticipated from the bifurcation analysis in Figure 3. Beyond the crisis point L, rotational motions are not high enough to cross the threshold HT unless a value of L is chosen from another shaded box just after the crisis from the opposite direction. Selecting L equals 1.001 from the intermediate range far from the crisis points L and R, the chaotic trajectories do not cross the threshold HT, validating the understanding. As the authors move further toward the point R, L approximately equals 1.00218, they expect the emergence of large amplitude rotational events, consistent with their analysis. Histograms in Figure 6 illustrate the rotational and librational dynamics in semilog scale, collected over long iterations of length $10, with a transient of $10, A clear distinction is observed between librational and rotational motion, with librational motion corresponding to the left group of bins and rotational motion to the right group. The extreme rotational event qualifying threshold $HT equals mu plus 6 sigma distinguishes extreme rotational events, ArXiv, from chaotic rotational dynamics, where mu is the sample mean and sigma is the standard deviation of the sample. Rotational events on the left of $HT are considered ArXiv. The probability density functions, PDFs, of the intravent intervals, IEI, between consecutive ArXiv are presented in Figure 7, where the numerical data, blue bins, fits well with the continuous exponential distribution, black line. The distribution is positively skewed, indicating that small intravent intervals have higher probabilities of occurrence of ArXiv, but the probability of ArXiv reduces significantly as the intravent intervals increase. Simulations are performed with parameter values lambda equals 0.999941, 0.999945, 1.001, $1.00218, and $1.0021884, with initial conditions $q_0. $q_0 equals 0.01, 0.02. The estimated rate parameter and standard error for each value of lambda are provided. The coefficient of variation, CV, is calculated to quantify the dispersion of the IEI. To study the occurrence of ArXiv, specific values of lambda are selected, including lambda equals 1.00218 at the crisis point R, where ArXiv are expected to occur. The grouped data in Figure 6, D, confirms the occurrence of ArXiv. The bifurcation diagram in Figure 3 illustrates that there are no rotational events beyond this crisis point R, and hence, no ArXiv can be anticipated. Two particular values of lambda equals $0.999945 and lambda equals $1.00218, are chosen to study the probability distribution of IEI, corresponding to the emergence of arrays. The authors analyze the histogram of accumulated data, excluding the initial transient, and find that it closely follows an exponential distribution, as depicted in Figure 7. The probability density function, PDF, of the exponential distribution is defined by equation 2, where lambda represents the rate parameter. By calculating lambda and its standard error for two subfigures, they discover that the standard error is larger in subfigure A, due to the limited number of extreme rotational events, arrays, in the gathered data. The coefficient of variation, CV, is also calculated, yielding a value close to unity, which confirms that the accumulated data adheres to an exponential distribution. The author's work demonstrates the effectiveness of selecting a suitable pendulum length to produce large amplitude rotational motion in a forced damped nonlinear pendulum. They successfully characterize librational and rotational events using bifurcation analysis, revealing that the system exhibits both rotational and librational dynamics, with occasional extreme events emerging in the rotational dynamics. Future research directions are proposed, including the investigation of chaotic saddles, coupled nonlinear pendula, and the experimental observability of extreme rotational events. The authors acknowledge funding from the Science and Engineering Research Board, SERB, and express gratitude to various individuals for their support and discussions. They declare no conflicts of interest and make the data supporting their findings available upon reasonable request from the corresponding author. This list appears to be a compilation of research findings and methodologies related to the field of computational linguistics. It highlights various studies on natural language processing, machine learning models, and their applications in different domains. The first entry discusses the development of a new deep learning model for sentiment analysis, which outperforms existing models in terms of accuracy and efficiency. This is followed by a study on the use of reinforcement learning for optimizing dialogue generation in chatbots, demonstrating significant improvements in conversational coherence and relevance. Another entry explores the application of transfer learning in NLP tasks, showcasing how pre-trained models can be fine-tuned for specific tasks with minimal additional training data. This section also includes a discussion on the importance of domain adaptation techniques to enhance model performance across different datasets. A notable mention is made of recent advancements in transformer-based architectures, particularly their ability to handle long-range dependencies more effectively than traditional recurrent neural networks. These models have shown promising results in tasks such as language translation and question answering. The list also touches upon the growing interest in multimodal language processing, where visual and auditory cues are integrated with textual information to improve understanding and interpretation. This area holds potential for applications in areas like image captioning and speech recognition. Furthermore, there is a focus on ethical considerations in NLP research, emphasizing the need for transparency, fairness, and privacy-preserving mechanisms. This includes discussions on bias detection and mitigation strategies, as well as the development of more interpretable models. Finally, the page concludes with an overview of future directions in NLP research, including the integration of cognitive science principles and the exploration of new neural network architectures. These advancements aim to bridge the gap between human language understanding and artificial intelligence capabilities. The analysis of complex systems reveals the importance of considering both linear and nonlinear effects to understand their behavior. This is particularly crucial for systems exhibiting chaotic or non-stationary behavior, where traditional linear analysis may be insufficient. The role of synchronization in complex systems is also highlighted, leading to emergent behavior and self-organization. Various measures, including mutual information, phase synchronization, and generalized synchronization, can quantify synchronization. Dimensionality reduction is a critical aspect of analyzing complex systems, as it enables the identification of underlying structure and dynamics. Techniques such as principal component analysis, PCA, and independent component analysis, ICA, are effective tools for reducing high-dimensional datasets. However, current methodologies have limitations, and new statistical tools and algorithms are needed to address the unique challenges posed by complex systems, including non-stationarity, nonlinearity, and high dimensionality. The authors acknowledge the contributions of previous studies, such as Govindan et al. 2009, Instantanium and Kant's 2008, to the understanding of complex systems. They emphasize the need for further research to develop methodologies that can effectively handle the complexities of these systems. By acknowledging the limitations of current approaches, the authors highlight the importance of continued investigation into the dynamics of complex systems. The significance of considering nonlinear effects in complex systems is underscored by the potential for emergent behavior and self-organization. Synchronization measures provide a means to quantify these phenomena, while dimensionality reduction techniques enable the identification of underlying structure and dynamics. Ultimately, the development of new methodologies and algorithms is crucial for advancing the understanding of complex systems and addressing the challenges they pose.